Okay, so we are talking about rotational motion. Things now are getting a little more realistic, right? As the quarter goes on, we're getting the tools and techniques where we can handle more and more realistic situations. Now our objects can have dimension to them and they can rotate. So we've talked a little bit about the fact that when things are rotating, there's all kinds of motion there now. They don't have to be moving. We can talk just about the pure rotation and the position of the points on something that's rotating. Right? We use angle theta to represent the position now. The angular speed omega, the angular acceleration alpha. We can deal with rotational motion exactly the same as we dealt with translational motion, using kinematics equations. And we saw that kinetic energy, when something's rotating, every little point, even though the center of mass is not translating, right, it's not moving, every little point on the object is rotating, is moving, I should say. And so each little piece of it has kinetic energy. And we can account for that, and we came up with this term, the kinetic energy, rotational kinetic energy, was 1/2 the inertia, now we use rotational inertia, times the square of the velocity, and we use angular velocity, right? That's strictly from something rotating. And then we talked a little bit about rolling. And because there's this nice fixed relationship when something is rolling, that the velocity of the center of mass is r omega, we can treat rolling. Let's go back to rolling here. Oops. There's two ways to view rolling. There's a complicated way and a way that's a little easier, I think. And the complicated way is that when something is rolling, let's draw a wheel rolling along a surface here. I guess I should make it touching the surface. There we go. What's really happening is that this is the axis of rotation. Oops. That point where it's in contact with the ground, that's the axis of rotation. And it's pivoting on that point that's touching the ground. And this is a little bit of a complicated way to view it because it's not rotating at its center of mass, and I mean, we could figure this out, and I'll give you a technique later on to show you that. But there's an easier way because we know there's this link between the motion of the center of mass and when something's rolling and the rotational speed. We can view it this way. So this is what's really happening, right? It's pivoting on this bottom point. So what's the velocity of the bottom point? If you were on the rim there, at the bottom point, you wouldn't be moving at all, right? That's the axis of rotation. Right? The wheel is pivoting on the point that's touching the ground. So if you were on the rim at that point, you wouldn't be moving forward at all. So the velocity in the forward direction of a point on the rim right there is 0. And if you were at the center of the circle, you'd have a velocity in this direction, v. And if you were up here, what would your velocity be to the right? It would be 2v, right? Because this thing is rotating, and when something is rotating and we want to know the tangential velocity of any point on that object, what is a tangential velocity? It's r times omega, right? So every point on a rigid object has the same omega. Every point has the same omega. If we're only a distance r away from the axis of rotation, the tangential velocity is r omega. If we're 2r away from the axis of rotation, the tangential velocity is twice as much, okay? So that's what's really happening when something is rolling. So we want a simpler way to view this. So what we can do, we can break this up. This is the velocity I should put here. This is the velocity of the center of mass, right? And this is 2 times the velocity of the center of mass. So this is kind of complicated. Let's see if we can split this up into two different components. Well, one will just be pure translation. Right? So in other words, it's moving without rotating. And the other one will be pure rotation. Okay, so no translation. And I'm going to show you that if we put these two together, we get rolling. So pure translation, no rolling. That means we've got our object here just moving to the right. V center of mass, V center of mass, V center of mass. Right? The whole thing is moving to the right with the same speed and nothing's rotating. Pure translation. Pure rotation means it's just spinning without going anywhere. All right, that's spinning. Spinning, not going in anywhere. Moving without spinning. If we combine these two, we add these two together, what do we get? We get the top of the wheel has a velocity of 2 v to the right. The midpoint has a velocity of v to the right, and the bottom point, the axis of rotation, has a velocity of 0. We get rolling. Okay, so I got a new computer. It's very touchy. Okay, so what we're going to do, instead of using the actual pivot point with the table, with the surface of the table, or the road, or when something's rolling, it's much easier if we say rolling is a combination of pure rotation and pure translation. So let's just look at a quick example.